Solving a problem on Brayton cycle, and Brayton cycle is we are considering ideal Brayton cycle. So this ideal Brayton cycle is a closed cycle, and the working fluid is air. So here you can see the question: a gas turbine power plant. So whenever we see gas turbine power plant, it is ideal Brayton cycle. Okay, we have ideal Brayton cycle in our syllabus. We don't have its modification. A gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. Now just see this. 1 to 2 is isentropic compression in the compressor. 2 to 3 is constant pressure heat addition in heat exchanger. 3 to 4 is isentropic expansion in turbine. And 4 to 1 is constant pressure heat rejection in heat exchanger. So here and here we have heat exchanger, here we have compressor, here we have turbine. And same way we have drawn TH diagram over here. So if you see the given question, what is given data? So you don't have to write this, just follow the problem. So it is mentioned that pressure ratio of 8. Now if you observe, P2 and P3 are same. Okay, so I'll just make a note of that. P2 is equal to P3. Same way, here you can observe P1 and P4 are same. So I'll write down P1 is equal to P4. So what is pressure ratio RP? RP is given as 8 and it will be P2 by P1, or I can write it will be P3 by P4. Okay, next data. The gas temperature is 300 Kelvin at compressor inlet. Now compressor inlet is 0.1. So T1 is 300 Kelvin. And then 1300 Kelvin at turbine inlet. Abhi turbine inlet is point number 3. You can observe here process 3 to 4 is turbine. So turbine inlet temperature is 1300 Kelvin, means it is zero point 0.3. So T3 value has been given. T3 is 1300 Kelvin. Next, it is mentioned here using the air standard assumptions. Basically, we have to consider air as working fluid in Brayton cycle. We are not considering, when we are supplying heat, we are not considering chemical reactions. Okay, here we are not considering chemical reactions. Here also, basically here heat is supplied using the source and heat is rejected using sink. That is there. So what we have to determine the gas temperature at the exit of the compressor. So what we have to find? To find part A, gas temperature at the exit of the compressor. So at the exit of the compressor means it is T2. So we have to find T2 and we have to find gas temperature at the exit of turbine also. Turbine exit means T4. So we have to find T2, T4. Next question B, we have to find back work ratio. Okay, back work ratio, what do you mean by that? See, here you can observe turbine work is more and compressor work is also more. And part of the turbine work is sent back to the compressor. So we have to find WRB, means work ratio, back work ratio. And it is given by equation compressor work upon turbine work. So that we can find. So I'll write down WRB, back work ratio. And last question which we have to find is thermal efficiency of Brayton cycle. So question number C, efficiency of Brayton cycle we have to find. So we'll complete this problem now. So in order to find T2 and T4, in order to find T2 and T4, we are going to consider process 1 to 2, which is isentropic, and process 3 to 4, which is isentropic. So I can write T2 by T1 is equal to, we know pressure ratio. So I'll write P2 by P1 raised to gamma minus 1 upon gamma. Okay, so I'll write down solution. T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma, and P2 by P1 is Rp. So Rp raised to gamma minus 1 upon gamma. Gamma for air we have to assume as 1.4. So from here I can write T2. T2 is equal to Rp raised to gamma minus 1 upon gamma into T1. Okay, Rp value is 8. So 8 raised to gamma minus 1 means 1.4 minus 1 divided by 1.4 into T1 is 300. So from here I can find T2, and T2 is uh, 543.43 Kelvin. Now next what we can do, we can consider process 3 to 4. So can you think what will be the equation? Just think this equation for 1 minute. So we can again use pressure ratio. So what we will do, we can write down this equation. We have to consider process 3 to 4. So I will write down T3 by T4 is equal to P3 by P4, which is Rp, raised to gamma minus 1 upon gamma. So I'll write down this equation. T3 by T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma. And what is P3 by P4? It is P2 by P1. And what is that? It is Rp, and Rp value is 8. So I can write down Rp raised to gamma minus 1 upon gamma. So from here, I can write, I want to find T3 value is already there with us. This is the T3 value. So I need to find T4. So T4 is equal to, so I can take T4 on this side and I will get T3 upon Rp raised to gamma minus 1 upon gamma. So T3 upon Rp raised to gamma minus 1 upon gamma. So just we will substitute the values. I'm audible, right? Huh. So T4 is equal to T3 value. We will write what was T3 value. T3 value is 1300. So 1300 upon Rp. Rp is uh, 8. 8 raised to gamma minus 1 upon gamma. Gamma for air is 1.4. So from here I can find value of T4, which is 717.6581 Kelvin. So this will be the answer. We had to we It was asked to find T2 and T4. So we have found T2 and we have found T4. Okay, what is the next question? Next question is work ratio. So back work ratio WRB. Work ratio means WRB. It will be equal to compressor work upon turbine work. So you have to remember this equation. So compressor work, how you will write this? This is small w and small t, t. So basically mass will not come in this equation. And if you see the compression, this is at compressor work, it is at it is isentropically. Okay. So this equation comes out to be Cp delta T. You can refer the first module 1 formula list. So it will be Cp and delta T for compression. What is delta T for compression? Higher temperature is T2, lower temperature is T1. So I can write down T2 minus T1. And turbine work will be again Cp, higher temperature. Higher temperature is, uh, here you can see on TH diagram, T3 minus T4. See, actually, how we get this equation, understand this compressor work and turbine work. Actually, it will be compressor work will be enthalpy at 3 minus enthalpy at 4. Sorry, compressor work 1 to 2. It will be enthalpy at 2 minus enthalpy at 1. And turbine work, it will be enthalpy at 3 minus enthalpy at 4. Similar to Rankine cycle. But for air, enthalpy is CPT. So basically, we are using this equation Cp into delta T for compressor. Okay, it's not like for compressor, the isentropic work is this equation. It's not like that. It is basically H2 minus H1 over here divided by H3 minus H4. And we are replacing this H1, H2 by Cp T2 minus T1. This can be done only for air, but remember that. Okay, we cannot use this for steam. Okay, that you need to note. So here Cp and Cp will get cancelled. And if you substitute the values, we have found all the values. T2 is 543.43. T2 value we have found over here minus T1 value, it is given in the question 300. So minus 300 divided by T3 value. T3 value again it is given in the question 1300. So 1300 minus T4 value, we have found here T4 value as 717.6581. So from here I can find WRB. This value comes out to be 0.418. This is second answer. Okay, what was the question? The question was the back work ratio that we have found. Now last question is the thermal efficiency. We have already derived the equation of thermal efficiency of Brayton cycle. So efficiency Brayton will be equal to 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. And it is equal to 1 minus 1 upon Rp is given as 8, 1.4 minus 1, 0.4 divided by gamma 1.4. So if you find this value, you will get it as 0.4479 and multiply by 100, you will get 44.79%. So this is efficiency of Brayton cycle. That is the end of the problem. Okay, now what I'll do is I'll add some extra part to this, which I'm not going to write and explain. I have already written that. So if you see this, I have added some extra part here. Okay, let me show you that part. Hmm. So you can see this. What is written here using compressor efficiency. So basically 1 to 2 is compression and 3 to 4 is expansion. So compressor efficiency, isentropic efficiency of compressor is given as 80 and turbine efficiency is given as 85. So we have already found this 2i and 4i value. Okay, which we calculated over here. This was 2i value or 2 value and the 4i value or T4 value we have already found. Now what we will write, understand this properly. See, since the isentropic efficiency is given, the process will not be isentropic. Because of friction, entropy increases. So point 2 will shift towards right. So we need to find new value of T2. Same way, during isentropic efficient expansion in the turbine, this is the process. But since the efficiency is given, it is not isentropic process. Because of friction, entropy is going to increase. And you can see point 4 has shifted towards right. So how I am going to write efficiency of compressor? I will consider smaller height upon larger height. So here you can see efficiency of compressor T2i minus T1 upon T2 minus T1. So here we know compressor efficiency it is given. T2i we had found out in the previous step. T1 is given. So I can find what is the new T2 value. The value of T2 which has shifted towards right because of the compressor efficiency. Same way 3 to 4i. 4i we had already found. Now we want to find 4. So I can write turbine efficiency. Smaller height T3 minus T4. upon larger height T3 minus T4i. So T3 minus T4 upon T3 minus T4i, we know T3, we know T4i, so we can find T4. And using, now see, the efficiency of Brayton cycle which we had used, it was 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. This equation is for isentropic process. Basically, this equation is for isentropic compression and isentropic expansion. If efficiency is given in the question, efficiency of compressor and efficiency of turbine, we cannot use that equation in terms of pressure ratio. So we need to go by the basic equation. What is the basic equation? Thermal efficiency of Brayton cycle is W net by Qs, and W net is Wt minus Wc upon Qs. So substitute the Wt value, Wc value as shown here, divide by Qs. We know all the temperatures, substitute those values, and from there you can find thermal efficiency. Now just note, if the process of compression is isentropic, means vertical, and expansion is also isentropic, just see what is the efficiency, 44.79%. But if we have isentropic efficiency of compressor and turbine being given, this efficiency value drops. And with these values of efficiency of compressor and turbine, 44.79 say percentage say efficiency has dropped to 27.41. Okay, so that is it with this problem. So today we have covered the numerical of Brayton cycle.